So in the last class, we are discussing about Markov chain, is it not? And then we discuss about the definitions of a Markov chain and certain examples, in particular simping queuing model. And then we have defined basically m-step probabilities and then one-step probabilities, Pij. And what we have seen that if you know the initial distribution and if we have, say, transition probability matrix P, then we can completely determine your Markov chain. Is it not? That means in any case, you can think of, you can find out the probability of xn is equal to k. Is it not? Or the combinations of others. Okay. So for the visualization things, we can think of my given Markov chain as a graph. So for the graph, what you know? We know that graph consists of basically vertices and then the edges. Is it not? So now if I give you, say, my state space S, which is, suppose I have, say, 1, 2, 3, and so on. Okay, this is my state space. And transition probability matrix, it is given to you, P. So now I can think of this S, this is all the vertices of my graph. And then see Pij, what is the? It is the probability from state I to j. Is it not? So now I can think of this. Suppose this is my state I and this is my state j. Then I can give a arrow sign, something that if it is directed from I to j, something like that. Okay, this is state I, this is state j, and this is my arc, which is directed from state I to state j, and then I can give a weight, which is nothing but my transition probabilities, Pij. So in this way, you can think of, or you can visualize this xn, which is a Markov chain, as a graph. Okay, so it consists of S, and then if I define these edges A, so this is S and A. Okay, so whenever there is no transition from state I to J, that means if Pij is equal to 0, in general we cannot put, we did not put this the arrow sign. Okay, so why this is important, it gives you the visualizations from state I to j, what is the probability and so on, so that we can later on we will study the classification of state I, okay, with respect to something that I will come back. But whenever we can think of Markov chain as a graph where S is the state space, okay, the point of the state space, and A is basically the set of all directed arcs from I to J, and Pij, this is the weight. Okay, so now I consider, okay, so we have defined Pij of n. I try to calculate this Pij, which is the n step or the m step. Okay, if I put m, this is the m step transition probabilities. So for that, I will consider the following theorem, which is called Chapman-Kolmogorov theorem. What it says that basically, suppose I want to know, so this is my state, say, J, and we have reached it at n step, and then we want to reach to state H, okay, maybe in n minus k step. That means I try to find out what is the probability of xn is equal to age given, or xk is equal to age. Okay, sorry, so maybe I can put it in this way. So if I have k is less than m is less than n is the bigger state, so xn is equal to my say state j. Okay, and I have started with xk is equal to h. So this is my at time k, I am in this state. So I want to reach at n state, okay, n time level with this state j. So what it says there, you can visit in m step in between all the points in the state space, and then you multiply these probabilities, then gives you the same. That means what it says that this is same as summation over I is in a probability of xn is equal to j given x of m is equal to state I. That means you visit at step m to all these states I, okay, I is in S, and then probability of xm is equal to I given x of k is equal to h. Okay, so you start with state H, you want to go to state J. So what it says that in between you can visit all other state, and then you consider the summations. That is means kind of the independence is there, and that is same as the probability of at time k you are having in state H, and if you want to reach at state j in time n. Okay, this is called the Chapman-Kolmogorov theorem or the equation. Let us prove it. So important thing is that k is less than m is less than n. Okay, how to prove it? This is simple. Already we know the properties of Markov chain, that the product thing we can write down. No, that summations over probability of corresponding things. So I can start with something like that. Probability of xk is h and x of n is equal to j. So this part actually I can write down. This is my summation over I is in S, probability over xk is equal to h, x of m is equal to I, and x of n is equal to j. Is it not? Because this is the total probability I can have. And these things I can write down. This is summation over. Now you see that this xk is equal to h, x sum is equal to y, xn is equal to j. So then I can write down using your previous thing I have done it. This summation over I is in S, probability over xk is equal to h, which is kind of the initial you can think of, and then probability of x of m is equal to I given xk is equal to h, and then probability over xn equal to j given x of m is equal to I. Is it not? The lemma we have proved it that if you consider the intersection of things, then that is same as probability of x0 is equal to I, and then probability of x1 is equal to some I1 given x0 is equal to these things, and then the product of that part, no, corresponding conditional thing. So I am exactly writing down from here to this part. So initial thing you can think of, this is xk is equal to a. Is it not? Because here you have only the three time points n, m, and k. So I have this part. So this implies what I can write down, that probability of xk is equal to h, xn is equal to j divided by probability, because this is summation is over I, so I can have probability of xk is equal to h. This is same as summation over I is in my s, probability of xm is equal to I given xk is equal to h, and then probability of xn is equal to j given x of m is equal to I. So this is precisely the right hand side, is precisely the right hand side of my my equation, Kolmogorov equations. So now the left hand side is nothing but exactly same as my this part. Is it not? This is probability of xn is equal to j given xk is equal to h. Because this is the conditional probability, so you can write down in this form. So this is more important because we want to calculate the m step probability. Okay, so for that I need this Chapman Kolmogorov equation. Why this is important? You see, so from this theorem, what I can say that for all nm maybe say greater equal to 0 and the state ij which in my S, then I can write down my Pij of n plus m. This is same as my summation over k is in S, Pik at step n, Pkj at step n. Is it not? Exactly that is why we try to write down here because this is the things I can write down nk minus k. So now this holds for any k less than m less than n. So accordingly I can think of we can start with 0 and then n is replaced by n plus m. That is exactly because we are considering a homogeneous Markov chain. So this is exactly your Pij of n plus m, and accordingly you can change it here. So this is the things. So now in matrix notation, what I can write down? So what is your Pn plus m? This is the matrix which has the element Pij n plus m. Is it not? And this one is nothing but the element as a. So if you look at that Pn and then P of m, this is a matrix. This is a matrix. So the product of matrix and the element of the product of matrix is exactly like this. So this is nothing but my P of n and then P of m. Okay. So what it says that P of n plus n as a matrix which is same as my Pn and then P of m. This is the matrix multiplication. So in particular, I can think of P of n, that is my P1 and P of n minus 1 for say n greater equal to 1, and P of 1 is nothing but my one step. So this P of 1, which is actually my P, which is nothing but the one step transition matrix. Is it not? So, and then you have P of n minus 2. So now again I can write down P of n minus 1 is P and then P of n minus 2 and so on. So what you have, if you do this thing, this is P and then P of n minus 2 and so on, then this is nothing but Pn. Is it not? So that means basically n times multiplications of your one step transition matrix. P times P times P into P n times. Is it not? So the n step transition matrix you can write down in terms of the matrix multiplications of one step transition matrix. Okay. So as a corollary, I can think if I know the initial distribution, so I have a Markov chain Xn, which is a Markov chain with state space S, and pi is the initial distribution. That means what is this pi is equal to my pi of I. What is your pi of I is equal to probability of x0 is equal to I. Is it not? So I is your state space. So then what I say that for all n greater equal to 1, I can find out the probability density function means mass function here, not density, because it is discrete. That probability of xn is equal to k for each k is in my S. This can be given in terms of the initial distributions and my n step probability, transition probability of n step transition probability. Okay, so this is summation over j is in S, P, J, K, N, and then by j. This is really important if you want to find out probability of xn is equal to k, then I need the n step transition probability of jk and pi j, and then you sum it up over j is in your state space S. How to prove it? Proof is simple. So probability of xn is equal to k. What I can write down as a total probability, that maybe start with any j and j is in my S. Probability of xn is equal to k and x of 0 is equal to j. So now these things what I can write down, you can use our previous lemma. This is summation over j is in S. This is actually I can write down probability of x of 0 is equal to j. Now I have two, n and 0, and another is probability of xn is equal to k given x of 0 is equal to j. So this is nothing but this is kj p of k, because we all are considering homogeneous Markov chain. This is same as summation over j is in your state space S. This one is nothing but your pjk at step n. So this is pjk of n, and this is nothing but my pi of j. Okay. So probability of xn is equal to k. This is same as summation over j is in S, p and jk. Let us consider one example, then it will be clear. So for that we will use these properties. So xn is a Markov chain with state space. This is your, okay, I put as a dt mc with state space S, which is say 1, 2, and 3. Okay, and my transition probability matrix, one step transition probability matrix, already you have seen my previous theorem that if you want to calculate the n step probability, then you need to know the one step transition probability is enough. Is it not? So suppose p is given to you, it is given say 0.3, 0.4, 0.3, 0.6, 0.2, 0.2, 0.5, 0.4, 0.1. You can consider whatever you want, so that it satisfies the summation over j, pij is equal to 1 and pij is equal to 0. So I'm just considering this part, and initial condition say pi, which is I have 0.7, 0.2, say 0.1. Okay. So then question is find I want to find two things. One is what is my probability of x2 is equal to 3. So whenever I am considering probability x2 equal to 3, if you look at your previous thing, probability of xn is equal to k, I need pjk of n. That is the element of your n step probability transition probability matrix. So that means I am having n is equal to 2, so I am to find that p2. This part I want to find, and this is nothing but basically p times p. P is your transition one step transition probability matrix, which is given to you. Okay, and second I want to find out that probability of x3 is equal to 2, x2 is equal to 3, x1 is equal to 3, and x0 is equal to 2. This part already you have seen it, in my previous example. Initial conditions and transition probability matrix is given to you so that I can find out these kind of things. Okay, so let us first try to consider, try to find out this A. So as I told you, I need to find out the two-step transition matrix, no? So for A, need to find two-step transition matrix P2. So this is nothing but my P times P. So now if you do this matrix multiplication, you check yourself, I may be wrong, it will be something like that 0.48, 0.32, 0.2, 0.4, 0.36, 0.24, then 0.44, 0.32, 0.24. Okay, this is my the two-step transition matrix. So as long as I know the two-step transition matrix, and in this case, what I have state space which is 1, 2, 3. So probability of x2 is equal to 3. This should be by definitions j is equal to 1, 2, 3, pj3, 2, and then pi j. Is it not? So if you calculate, it should be something like that, 0.212. Okay, you calculate it. So it will be something like that. Okay. And what about the other things? Probability of x3 is equal to 2. Sorry, x2 is equal to 3, x1 is equal to 3, x0 is equal to 2. These things actually I can use your previous things, the lemma, what is x0 is equal to 2, then probability over x1 is equal to 3 given x0 is equal to 2, then probability of x2 is equal to 3 given x1 is equal to 3, and then probability of x3 is equal to 2 given x2 is equal to 3. Is it not? So this is nothing but probability of x0 is equal to 2, and then this one is p23, p33, and then p of 32. So p02, this is basically nothing but pi of 2. Now pi is given to you, so pi of 2 is nothing but 0.2. So now if you calculate, and p23, p33, p32 you can find out from your transition probability matrix P which is given to you. Is it not? Because this is something you can write down 1, 2, 3, 1, 2, 3. This is 1, 1, 1, 2, 1, 3, and similarly you can find out. So now you check it. This should be something 0.0016. Okay, you calculate yourself. Okay. So what it says that to find out m-step transition probability, we need so-called the Kolmogorov-Chapman or Chapman-Kolmogorov equations, and from there we have seen that P of n, which is nothing but that the matrix multiplications of P n times, where P is one-step transition matrix. And not only that, if I know the initial distribution along with one-step transition matrix, then we can find out the probability mass functions of your given Markov chain. Okay, so now I discuss so-called the classification of states. What it says that, so I have a Markov chain Xn, which is my DTMC with state space, say S. Okay, so it may be finite, it may be countable. Okay, it states S. So there is a definition called accessibility. That means, say I have a state J. Okay, so this state J, whether it can be accessible from state I or not, that is actually we want to know. So we denote as something like that I is J is accessible from I. This is my notation. Okay, I is accessible in this array. So if I can find a n greater or equal to 0 such that my Pij of n in 0, that means if we start with state I can reach it state j in n state. okay, with positive probability. That means Pij of n for some n. So that means basically that state J is accessible from state I. Okay, and there is called the communicates, means two states communicates or not. Again, I have state I have state J. So what it says that if your state I is accessible from state J and also J is accessible from your state I, that means two states communicates each other. So if two states I and J are such that J is accessible from state I and I is accessible from state J, then we say that two states I and J, they communicate each other. So that means what? That means basically I can find say N and M such that Pij of say N is positive, Pji of M is positive for some Nm greater equal to 0. Okay. And there is another concept called, so suppose I am a state I, it may possible that I cannot go from that state to any other state. In particular, that is called the absorbing, means it absorbed there. We cannot go from that state to any another state. You cannot communicate. So that is called the absorbing. So a state I is said to be absorbing if that means Pii, which is actually is equal to 1. So if it is 1, actually there is no probability. No, I cannot go to other state. That is why it is observed there. Okay. So this relation, no, it gives you somehow the relation. So this notation I put, something like that, this one, and then this is the notation. So if I and J communicate each other, we noted that I communicate. This is the notation I am having. So you can check yourself that this relation or your accessibility relation, it is transitive. Okay. It is simple lemma. I am not going to prove it. It is nothing else actually. The relation, this one, is transitive. This is, you can expect, no? Because of your Raman-Kolmogorov equation, you can expect these things. What it says that means what it says that if my state say J, it is accessible from state I, okay, and my state K, which is accessible from J, then I can expect that my state K should be accessible from I. Okay, and similarly that the communicative things also, if you look at this also relation, then that is also transitive and so on. So this is just nothing but your common Chargaff equation. Why this is so? Suppose I have these things. J is accessible from state I, K is accessible from state J. I want to know whether state K is accessible from state I or not. So what it means? That means I can find some say R and L such that Pij of R is positive and this is Pjk of L is positive for some R and L. Is it not? Because of this one and because of this one. So now what I have to consider? I have to say that P of Ik. Now if you look at L plus R, okay, by using your Kolmogorovs, what I can think of, I can consider any state say J is in S. This is Pij R Pjk of L. So this is the total sum and all are the probabilities. So this is non-negative. So this one, this is total sum. This is same greater than or equal to Pij of R P jk of L, and this is positive, this is positive, so the product is positive. Okay, so that means this relation, they are transitive. Okay, not only that, you can check that this this relation, okay, common degree relation, it is actually an equivalence relation over S. Since it is a equivalence relation, we can define a equivalence class. Okay, so I can think of as a remark the relation is transitive, and if I and J they communicate each other, is or this relation is an equivalence relation. You know the definition of equivalence relation. Okay, it is symmetric, it is transitive, and so on. So you have this over my state space. So what is say that I have a state, now I have a say set S. So this set S is considering the equivalence class. Okay, so I can define what is the equivalence class now. If I denote by C of I, which is the class, that means it forms a partitions of S. So what is my I? So although J is in my set S such that I and this J, they communicate each other. So we put there in a same set. Okay, in the equivalence class where I is in your set S. Okay, and you check because of all this relation that Ci, it forms a partition of S. So with respect to this partition, we will have a characterizations of a Markov chain that is called irreducible. So I'm putting as a definition. So a Markov chain is said to be irreducible. Irreducible, we cannot reduce it in the sense that means basically we have only one equivalence class, which is basically your full set. Okay, if the state space consists of only one class. Okay, so what is mean? Only one class means basically all the states, they communicate to each other. Is it not? That is, all the states communicates to each other. Is it not? That means if we consider any two states, I and J, they communicate to each other, and hence all the states communicate to each other. Okay, let us consider one example whether we can have a irreducible Markov chain or not. So that means we have to show that my state space contains only one equivalence class. So I consider Xn, which is a DTMC with state space say 1, 2, 3. Okay, and my initial distribution, though I don't need initial distributions here, the transition matrix P I am having say 0, 3 by 4, 1 by 4, half, 0, half, 1, 0, 0. Okay, so I'm saying that Xn, then Xn is irreducible Markov chain. So now you see the transition, if you look at the transition graph, how to find out this transition graph? So I have this 1 and 2, and 3. This is my state space. So now what is given to you from state, you just look at here. From 1 to 1 it is 0. So whenever it is 0, actually we are not giving any directed arc there. So from 1 to 2, 1 goes to 2, 1 goes to 2, what is the weight? That is 3 by 4. Is it not? And then you have 1 goes to 3, this is 1 by 4. So I am considering 1 goes to 3, 1 to 3. This is the things, no? That P13, which is 1 by 4. That means from state 1 to state J, they are accessible and with probability which is given by 1 by 4. Okay, so now what I can have, this is 2 goes to 1, which is half. So 2 goes to 1, this is half. 2 goes to 2, this is 0. And then 2 goes to 3, this is with probability half. So 2 goes to 3 with probability half. Okay. Similarly, 3 goes to 1. So 3 goes to 1. That is with probability 1. Hence, actually, from 3, we cannot have anything because 3 goes to 0 and 3 goes to 2 and 3 goes to 3. They are with probability 0. So there is no work. So this is called the transition graph. Okay. So why this transition graph is more important? As I said, that the visualizations from here. So now here, if you see from the transition graph, that 2 goes to 3, 3 goes to 1, no? 2 goes to 3, 2 goes to 3, 3 goes to 1. Hence, I can say, and 1 goes to 2. 1 goes to 2, no? 1 goes to 2. Hence, I have 3 goes to 2. 3 goes to 2. Is it not? Thus, 3 and 2 are equivalent because 3 goes to 3, 3 goes to 2, 3 and are equivalent. So now you check it easily. What is my C of 1? This means although J is in S such that 1 is accessible to, means 1 is communicated to J. Is it not? So now this is nothing but actually all 1, 2 and 3. So what it says that J 2, so 1 goes to 2, 2 goes to 1 you have. And all these things, just look at the transition graph. From there, actually, I have C1, which is 1 to 3. And similarly, you check it C2, C3, they are basically same. So I have only one equivalent class, okay, or one class. So hence, this Markov chain is a irreducible Markov chain. Okay. So we have another concept that is called the returning state. Returning state means basically you start with state I. So is there any probability, means is there any possibility that you can return to again state after certain times later? Okay, so that means what it says that as a definition, these are the we want to know. No, suppose you start with state I. So after some point, whether you can return to the state or not. So what do you mean by returning state? So suppose my state I, which is fixed. Okay. So I said that return state. So state I is said to be return state if Pii of n is positive for some n greater or equal to 1. Is it not? Because what is this? This is basically you start with say x0 is equal to I, given I want to have x of n is equal to I. That probability. This is exactly this part, no? So means you initially start with state I. At step n, for some n, can you again return to state I or not? If it is possible, then we say that this state I is called the returning state. Okay, so you may have many possibilities. Means you can have state n, and n state you can find out, because this is for some n. Suppose you have set some 2, maybe somebody has 4, somebody has 6, and so on. So for that case, if I is a returning state, then I can think about the period. So the period of I is defined by, I denote as a lambda I. This is nothing but the GCD, means the minimal way. Okay, GCD of all those n such that PII of n is positive. Is it not? Because this said that for some n, it is I is returning state, we know. So maybe you are coming here. So first time actually you reached. That is something like that. Lambda I, which is the not the first time. Sorry, this is the GCD of that part. Okay, that is the period. So as I showed the 2, 4, and 6. So now you see that GCD should be 2. Because on the period of I, we have one more classifications. So that is called the aperiodic. The state I is called aperiodic if lambda of I is equal to 1. Okay, that means GCD of n such that Pi of n is greater than 0 is equal to 1. And a Markov chain where all the states are aperiodic is called aperiodic Markov chain. So a Markov chain with all states aperiodic is called an aperiodic Markov chain. Okay, I'll come back to example that whether there exists a aperiodic Markov chain or not. Okay, so before that, it is interesting to see that suppose I and J, they communicate each other. Okay, then what can you say about the period of state I and J? Intuitively, it should be same, no? Because since I and J, they communicate each other, that means if I is a returning state, J should be also returning state, and because of the GCD and so on, so they should be same period. But actually, it is same period. So this is the theorem. If I and J, they communicate each other, then the period of I is same as period of J. Okay, so proof is again simple. Just you need to use the Kolmogorov, Chapman-Kolmogorov equations to find out these things, and then the properties of GCD and so on. Okay, so I'm not going to prove these things. So this is easy. I left as an exercise. Okay, so now we talk about so-called the first visit and mean passage time. So what does mean that? So now we start with, suppose you start with state I. Okay, so initially you start with state I. You want to visit at state n, sorry, at time n to state j. That means xn given j the first time. That means x of k in between, this is not equal to j for 1 less equal to k is less than n minus 1. In start with state I, first time you visit state j in n state. That we denote as f of ij of n. What is the probability of these things? That we denote as a fij n. That means it is the probability that the starting with state A, the first transition to state j, which occurs at time n. Is it no? And by definitions, I am defining fij of 0, which is actually 0. And I am defining f of ij, which means starting with state I, the probability that we ever making a transition from state j. So that means summation over n is equal to 1 to infinity f of ij of n. Because fij of 0 is equal to 0, so n is equal to 1 to infinity fij n. So fij is nothing but it is the probability of ever making a transition into state j, given that you start with a state I. Means x0 is equal to I, and you first time you visit state n, and fij is summation over this part. Okay. So now question is there any relation? I have fij n, which is basically first time, and I have pij of n already. Is it not? The n step transition probability is pij n. So this is nothing but what? This is basically probability of x of n is equal to j given x of 0 is equal to I. But we are not saying that the first time whether means if it is the first time, then this is fij of n. Okay. So you check that fij k of n is equal to 1. This is same as my p of jk. So is there any relation between this fij n and then pij n? That is called, this relation is called the first entrance theorem. The following holds. There holds that pjk of n you consider from r is equal to 0 to n. You start with fjk of state r and then pkk of n minus r for n greater equal to 1. This is called the first entrance theorem, and hence because f of jk of 1 is nothing but my p of jk. Okay. So what is the relation between pijkn and fijkn, which is given by the first entrance theorem? Okay. So I try to also know what is the mean passage time. Mean passage time means I am defining mu jk, which is summation over n is equal to 1 to infinity n f of jk of n. Okay, this is the mu jk, what is called the mean passage time. But we are mainly interested when j is equal to k. So we are basically interested j is equal to k. That means suppose your state j is a returning state, and then what is the mean time one required starting with state I, you return to again state I. Okay, what is the mean time? Because this is a random variable. So I can think of, as I said, that we are interested for j is equal to k. That is more interesting thing. And in that case, that fjj, whenever j is equal to k, this is fjj of n. So what is the fjj of n? It represents nothing but the distribution of the recurrence time of state j. Okay. So for j is equal to k, I have to write down mu jj, but for short notation, I put as a mu j. So mu j is nothing but summation over n is equal to 1 to infinity n times f jj of n. Okay, so this mu j I can think of, as I told you, that it is a expected return time of the chain to state j. How to visualize that part? So for that, I am defining this following random variable tj, which is exactly same thing else I wrote down, that infimum of n greater equal to n such that xn is equal to j given x0 is equal to j. Okay, so now this tj, which is basically the first time it visits state j, starting with state j. So then mu j you can think of, this is expectation of tj. Okay, so tj, it is the expected return time of the chain to state j. Okay, so always given the state, I mean the chain started from state j. Okay, so start with state j. What is the expected return time to state j? That is given by mu j. So depending on the value of mu j, we have another classification that is called the recurrent state. So I am considering the definition. So a state j, which in my state space S, is said to be recurrent if f of jj is equal to 1. So what is your f of jj? That means that starting from state j, okay, the transition to state j ever making is always possible. That is f of jj, no? F of jj already we have defined it. F of ij is equal to summation over n is equal to 1 to fij of n. This is the probability of ever making to state j, starting with state j. So that is called, it is certain. Is it no? Because fjj is equal to 1. That probability is 1, means always you can returning to state j. So that is why this state j is called the recurrent. Okay, you are coming back to that. Otherwise, it is called transient. Otherwise, it is transient. Okay. Otherwise, it is transient. So now, if I have a recurrent, then I have classifications of recurrent, that is in terms of my expected recurrent time, or in particular in terms of mu j. What it says that the recurrent state j is positive recurrent if mu j is finite, and it is called null recurrent if mu j, which is infinity. Okay, so now one can check that f of jj is less than 1, okay, which is not certain. This is equivalent to say that probability of tj is equal to infinity with some positive probability. That means we consider not tj, which is the infimum of n, such that xn is equal to j given x0 is equal to j. Okay, that means this tj, that should be infinity with certain positive probability. Okay, because f of jj is equal to 1, that is certain, and hence probability of tj is equal to infinity, that is positive. Okay, so let us consider one example. and then we'll see. So you consider Markov chain with state space. This is a DTMC with state space S equal to say 0, 1, 2, and 3. Okay, so 4 point is there, and the transition matrix P is given to you. This is 0 0.8, 0, 0 0.2, 0, 0, 0, 1, 0. You can make yourself many examples. 1, 0, 0, 0, 0 0.3, 0, 0 0.4, 0, 0 0.3. Okay, this is the transition matrix. It is given to you. So you want to classify the states of the given Markov chain. So what will be your transition graph first? Then it will be easier, no? So this is say 0. Okay, this is 1. This is 2. This is 3. So 0 to 0, this is probability 0. So this is the something like that. I wrote down 0.8. 0 to 1, no transition. 0 to 2, there is a transition 0.2. Okay, this is 0.2. And then 0 to 3, no. 1 to 0, no. 1 to 1, no. 1 to 2, I have a transition. 1 to 2, that is with probability 1. Okay, and then 1 to 3, no. Then 2 to 0, yes. So 2 to 0 with probability 1. So other things there is no. So now 4 to 0, there is a transition. Sorry, 3 to 0, there is a transition. So this is your 3. So what is the probability? That is 0.3. Then 3 to 1, yes, there is a transition. That is 0.4. And then 3 to 2, no, but 3 to 3 I have, which is 0.3. This is the transition graph of your given Markov chain. Okay. So now I want to find out the classifications of states in the sense that whether the states are transient, recurrent, and so on. So now look at what I have to find out. I have to find out that mu f22, whether it is 1 or not. So what is my f of 0, 0, 1? This is nothing but my p of 0, 0, which is actually 0.8. So what is my f of 0, 0, 2? 0, 0, 2 means in a 2 times 2 state. Okay, in a 2 state, it reaches starting with state 0, it will reaches here. So now what is the probability? So from here 0, it can go to 2, and then from 2 to 1. So this is probability 0.2, and then this is 2 to 1, actually 0.2. Is it not? And what is f of 0, 0, 3? Or I can put as a n, which is actually 0 for n greater equal to 3. Because it start with 0, it will come to here, okay, and then it cannot go to other state to go there. So it will go to here from here. So that means minimum 3 step I can't have. So that's why f of 0, 0, n is equal to 0 for all n greater equal to 3. Is it not? So this denotes basically only in step 1, only in step 2. Okay, starting with state 0, it will again reaches to state 0, and so on. Okay, so what is your f of 0, 0? That should be by definition summation over n is equal to 1 to infinity n times, what is your definition of f of I, fij, yeah, this one, no, fij of n, not n. That I will come back later. This is f of 0, 0 of n. Is it not? So now n is equal to 1 and 2, which is 0.8 plus 0.2, which is exactly 1. So f of 0, 0 is equal to 1. That's mean what I can say, the state 0, what you can talk about, that is basically recurrent. That is by definitions, no? F of jj is equal to 1. So state 0 is recurrent. Similarly, you check state 2 is also recurrent. Okay, so let us consider what about state say 1. So what I have, f of 1 1 n is equal to 0. Yeah, look at here, from 1 it is not going and not coming also, because it is coming from here, here and so on. So state 1, f of 1 1 is equal to 0, hence this implies f of 1 1 is equal to 0. Okay, so similarly you can also find out what is my f of 3 3 of 1, which is nothing but 0.3, and f of 3 3 n, which is 0 for n greater equal to 2. Hence I can have f of 3 3, which is summation over n is equal to 1 to infinity, f of 3 3 of n, this is less than 1. Hence my state 3 is transient. So state 2, state 1 and 3 are transient state. Okay. Okay. Similarly, you try to find out from there that whether it is positive recurrent or not, because 2 is recurrent. So we have considered 1, this part, no? Let us take 0. So now what I have to put mu 0, this is summation over n is equal to 1 to infinity n, then I have f of 0 0 n, no? So now you see that that is finite, no? Because f of 0 0 n for negative equal to 3, this is 0, so this is finite. Hence state 0 is positive recurrent. Is it not? State 0 is a positive recurrent. And similarly, you try to also find out for state 2. Okay. Okay. Similarly, you can find out many examples about, say, whether there exists a null recurrent or not, and so on. In particular, I'm giving you that things. And one more example. So I have a Markov chain, say xn, with state space n, natural number. Okay, and the transition properties are given like this: p01, which is 1, pi0, which is 1 by I plus 1, and pi2 I plus 1, this is I by I plus 1. Okay, for I greater equal to 1. So now you consider the state 0. So my claim is state 0 is null recurrent state. First you have to show that whether it is a recurrent or not. So you check it that f of 0 0 1, this is exactly 0, and f of 0 0 n, this is nothing but 1 by n into n minus 1 for any n greater equal to 2. Okay, just look at these transition things and then you try to find out. Just draw the graphs and then you will find out. So hence what I have, f of 0 0, this is nothing but summation over n equal to 1 to infinity, f of 0 0 of n, this is summation over n is equal to 1 to infinity 1 by n into n minus 1, this is check it, it should be 1. Okay, so what I have, that 0 is a recurrent state. Since it is recurrent, next step is to check whether it is a positive recurrent or null recurrent. That means I need to consider that mu of 0. This is nothing but summation over n equal to 1 to infinity n of f of 0, 0, n. This should be nothing but summation over n over n equal to 1 to infinity, which is actually infinity. Is it not? So this is a divergent series. Hence, state 0 is null recurrent. Okay, this is just one example. As I say that you can find out various examples. So, okay. So now, so we have state I, whether it is a recurrent or not. I have a definitions, but is there any necessary and sufficient conditions or not? Is it not? Because each time looking at these things, it may not be possible. So sometimes we need necessary and sufficient condition when a state J to be a recurrent or not. It is given by the following theorem. I'm not going to prove these things, but I will use some consequence of this theorem, okay, to discuss about the nature of the state. What it says that a state I is recurrent if and only summation over n is equal to 1 to infinity, you consider pi of n. Okay, that is finite. Sorry, this cannot be finite. This is actually infinity. Okay. So state I, which is recurrent, if and only this holds. Pijn, summation over n equal to 1 to infinity Pijn, that is infinite. So as a corollary, what I can say is the following. That is, you can expect that if I have a two states, suppose I and J, they communicate each other. Then if one is recurrent, then another would be also recurrent. So that is my corollary. If I and J are two states and they communicate each other, then I is recurrent if and only if J is recurrent. So let us look at the proof. See, I and J, they communicate each other. That means there exists a Mn positive such that Pij of n is positive, Pji of say n, that is positive. Is it not? So now I am looking for something like that. Summation over k is equal to 0 to infinity Pjj of n plus m plus k. Okay. So now these things using the Kolmogorov, means summation Kolmogorov equations, I can do this summation over k is equal to 0 to infinity. This is Pji of m, Pii of k, and then Pij of n. So now this is over sum. I can take out this is Pii. Sorry, I made a mistake. Over k, yeah, it is okay. So I can take these two out. This is Pji of m, Pij of n, and then summation over k is equal to 0 to infinity Pii of k. Okay.
I didn't catch that. Could you try again?
Okay. So now you see that if this one is divergent, that means if this is equal to infinity, then this should be divergent. Is it not? So that is why I say that the recurrent state, what it says that summation over k is equal to 0 to infinity, pi of k, that is equal to infinity. So if this one is divergent, then this should be divergent. So that means the I is recurrent if and only j is recurrent. Okay. That is we can expect, no, because I and j, they communicate each other, and hence you can think of that if I is recurrent, then j should be recurrent. Okay, one more easy consequence of this is the following. What is summation over n is equal to 0 to infinity pij of n? This I can write down summation over n is equal to 0 to infinity. This is probability of x of n is equal to j given x of 0 is equal to I, is it not? So now these things actually I can write down as a characteristic function. Summation over n is equal to 0 to infinity. Expectation over characteristic function over xn is equal to j, okay, given x of 0 is equal to I. So now this is characteristic functions and so on. So you can interchange the expectation and limit. So this is expectation of summation over n equal to 0 to infinity. Characteristic function over xn is equal to j given x of 0 is equal to I. Okay. So what is this? That means basically this is nothing but the expected number of visits that the chain makes to state j starting at I. You know, that is the thing. The expected number of visits. So this is nothing but expected number of visits that the chain makes to state j starting from state I. Okay, starting at I. So therefore, what I can say that previous theorem, what it says that summation over n is equal to 1 to infinity, pii of n is equal to infinity. So that means it says that a state j is recurrent if and only the expected number of returns is infinite. Okay, state j is recurrent if and only if the expected number of return is infinite. Okay, so that is a state j is recurrent if and only if the expected number of return is infinite. Okay, so one more thing actually I can say here, that if my j is transient state, then summation over n is equal to 0 to infinity pij of n, this is finite for all I is in S. So if J is a transient state, then by using maybe your first entrance theorem, we can show that summation over n equal to 0 to infinity pij of n is finite. So that means that limit n goes to infinity, pij of n is equal to 0 for all I is in S. So now I can think of, means have some asymptotic things. Now as n large enough, what happened? So what it says that for transient state j, limit n goes to infinity, Pij of n is equal to 0. This holds for all I is in your state S. Okay. So later on, we try to know what about if your state is recurrent. So this is for J, which is transient state. So from there I am having this part. Okay, because if your say J is recurrent, what I know that summation over n is equal to 1 to infinity Pjj of n, which is infinite. So from there actually you cannot say anything else, is it not? But here actually you definitely say if it is transient state, then limit n goes to infinity Pij of n is equal to 0. Okay. So as I said that we want to know, it's a natural question. So J is transient, then I am having this thing. So what happens if J is recurrent state? So which gives the limiting properties of the n step transition probabilities, which is given by the following theorem. I am not going to the proof of these things of this theorem, but I will use this theorem. What it says that, so if state J is positive recurrent, then as n goes to infinity, I have the following, that Pjj of n lambda j. Okay, I can talk about lambda j is nothing but the what is called the period of your state j. This is converges to lambda j by mu j, because since it is a positive recurrent, I know that mu j is finite. Okay, where j is periodic with period lambda j. Okay, j is periodic with period lambda j. So what happens if it is aperiodic? Okay, if j is aperiodic, then what happens? So for j is aperiodic, what it says that Pjj of n, this converges to 1 by mu j when j is aperiodic. Now it seems that in that case lambda j is equal to 1, so it is exactly similar kind of things, no? But means what I'm saying that it's kind of the it agrees for both cases. 1 by mu j when j is aperiodic. Moreover, if this converges to there, then you know from your calculus course that if you consider 1 by n summation over r is equal to 1 to n Pjj of r, that is also converges to 1 by mu j. Is it not? So because what it says that basically xn converges to some x, then you can consider that y of n is 1 by n summation over I is equal to 1 to n x of I. So that is also converges to 1 by mu j when j is aperiodic and also positive recurrent. Positive recurrent is given to you. And another is that if k is positive recurrent, aperiodic, then for every j that limit n goes to infinity Pjk of n, so k is positive recurrent and aperiodic. So that is actually mu jk by mu k. Okay, and if your state j is null recurrent, then Pjj of n, this converges to 0 as n goes to infinity. These are the not the classifications. The question is, what happens as n goes to infinity. So these are the various cases. What it says that if your j is positive recurrent with period say lambda j, then Pjj of n lambda j that converges to lambda j by mu j as n goes to infinity. So if it is aperiodic positive recurrent, then Pjj of n converges to 1 by mu j as if it is aperiodic. And not only that, I have these relations. Okay. So now I am considering the cross things. So because this is all jj. So cross thing means basically j and k. What it says that if you have a positive recurrent k and also aperiodic, then look at Pjk of n, limit n goes to infinity, that is nothing but the f of jk by mu k. Okay, because mu k is finite. This is okay, positive recurrent, that's why mu k is finite. And if j is null recurrent, then I have Pjj of n that goes to 0. Okay. Okay, I'll stop now, and then next class I'll talk about for the finite Markov chains and certain properties of that. Okay.